Hello everyone. What I'd like to do in this video is give you some more examples of transformations of the trig functions tangent, cotangent, cosecant, and secant. Now, while we already did vertical stretches in the last video, we didn't take a look at vertical stretches of tangent and cotangent. These ones here can be a little bit tricky. The reason for that is there's not a great feature on tangent and cotangent where you can easily tell that it's been stretched or compressed. For sine and cosine, it's pretty easy because you just think about their amplitude. If it's vertically stretched or vertically compressed. Cosecant and secant, they kind of have those parabolas that are kind of going up and down, and so you can think about those being vertically stretched or compressed. But for tangent and cotangent, their graphs kind of look like these kind of cubic shapes, stuff like this, and so it's kind of hard to see how they've been, stretched or compressed. So what I'd like to do is give you a tip for how can you draw vertically stretched or compressed graphs of tangent and cotangent so that the reader is able to tell that they've been stretched or compressed. So to do that, let's go ahead and draw a picture of the unit circle here really quick. Okay, so here we have the unit circle. Okay, here is 0 radians, here's pi over 2, and here is pi. Okay, so the coordinates here are what, 1 and 0. Here they'll be 0 and 1. Here they'll be at what, -1 and 0. And here they'll be at what, 0 and -1. Okay, and this is at 3 pi over 2. Okay, so remember, when we're thinking about the graph of tangent, let's just kind of draw a tangent here really quick, just a little bit more detail. Okay, for tangent, let's graph tangent of x. So the way I like to think about tangent of x is tangent is sine over cosine. So since sine is the y-coordinate and x is, and then cosine is the x-coordinate, sine over cosine will just be the slope of the line as we rotate around the unit circle. So a great way to think about this is tangent has an x-intercept at 0, or the tangent of 0 degrees is 0. And then what I said in the last video is it goes between x-intercept, and then when I'm at pi over 2, now the slope here is infinite, so I'll have a vertical asymptote. So it goes x-intercept, vertical asymptote at pi over 2. And then when we're back at pi, I'm back to a slope of 0. So it goes x-intercept, asymptote, x-intercept. X-intercept, asymptote, x-intercept. But what's nice is we can actually think about the spots in between here. So if we go halfway between pi over 2 and 0, we'll now be at pi over 4. Let's just mark that right here. We'll now be at pi over 4 if we go 1, 2, 3 pi over 4s. Okay. The x and y coordinate here are as root 2 over 2 and root 2 over 2. And the x and y coordinate here, let's see, the x coordinate is negative root 2 over 2 and root 2 over 2. Notice here that tangent of pi over 4, well, there's two ways to think about it. One, you could think of the slope of the line here is 1. Or if you think of sine divided by cosine, the sine and cosine are the same, so root 2 over 2 divided by root 2 over 2 will be 1. So tangent of pi over 4 is 1, and similarly, tangent of 3 pi over 4, well, over here, I'll have a slope of -1. So it'll be -1. And if we're going to be working with cotangent, it would be the same thing, because the reciprocal of tangent is what cotangent is. The reciprocal of 1 is 1, and the reciprocal of -1 is -1. So this would also be the same if we were doing cotangent. Cotangent of pi over 4 is equal to 1, and cotangent of 3 pi over 4 is also equal to -1. Okay, so what we can do here is we can think about these spots here in the middle. So here's pi over 4. Here's 3 pi over 4. So 1 pi over 4, 2 pi over 4s. 3 pi over 4s, 4 pi over 4s. Okay, so it's going to go x-intercept. So we can think about this. X-intercept, slope of 1. Infinite slope. Slope of -1. Slope of -1. Slope of -1. And then slope of 0. So we have these nice spots here where we can draw the graph. So tangent, at least one period of tangent, one period of tangent will look like this. Now, of course, you can either measure the period of tangent from 0 to pi. You could just take this picture and repeat it, and we'll get the nice graph of tangent. Or if you'd like to have that kind of nice cubic piece, you could think about one period of tangent being between negative pi over 2 and pi over 2, and here we'll mark negative pi over 4. So we'll have a vertical asymptote here, and then here it'll be negative 1. So notice if we were traveling negative pi over 4 units, that's us traveling this way. So right here, if you'd like, if we're traveling this direction, this is negative pi over 4. The x-coordinate here is root 2 over 2. The y-coordinate is negative root 2 over 2. So I hope you can see that tangent of negative pi over 4, the slope here is the negative 1, which we have right here. So it's going to be nice for us to keep track of these spots right here. So when I vertically stretch, I'm going to think about these spots being stretched outward. Let's do an example. And it would be the same thing with cotangent. And we'll do an example of that here in just a second. How about we just do it real quick? Let's just do cotangent really quick. So same idea with cotangent. Same idea with cotangent. I want to just add an extra piece of detail into the graph. Okay, so let's go over here to pi. How about pi over 2? Okay, so this is how when I'm first just drawing loose sketches, when I'm drawing loose sketches of cotangent. Well, what I remember is I remember that cotangent is a reciprocal of tangent. So if tangent started out with a slope of 0, so we have 0, so then so we have x-intercept, so 0, then vertical asymptote, cotangent, those will be flipped. So since tangent starts with an x-intercept, cotangent will start with a vertical asymptote here. So vertical asymptote, x-intercept, vertical asymptote. Okay. We'll go halfway in between here, so this will be pi over 4. This will be 3 pi over 4. Well, I know that cotangent of pi over 4 is 1, so we'll have a 1 here. And I know that cotangent of 3 pi over 4 is negative 1, so I'll mark that here. So we have these nice spots that help us piece the graph together. So here's a more detailed graph of cotangent of x. I've just kind of recorded 2 extra points here. So if I want to vertically stretch or compress this, I'm basically going to move these points. If it's stretched, I'll move them outward. If it's compressed, I'll move them inward. Let's do an example. Okay, so as an example, let's go ahead and let's graph at least one period of, how about y equals, let's do how about 3 times the tangent of, how about 4x? Go ahead and pause the video and give this a shot on your own. Okay, let's do it. First thing I'm going to ask myself is, what is the period of this function? So remember that tangent normally has a period between 0 and pi, or has a period of pi. So, one way to think about this is you could take pi and divide it by 4x, or divide it by 4, or you could say, well, I need the inside of tangent. When is that between 0 and 2 pi? I'm sorry, 0 and pi. And then if you divide everything by 4, you'll get that my period. I'll get one period of the graph between 0 and pi over 4. So our period is pi over 4. So let's go ahead and sketch that. Okay, so here we are at pi over 4. We'll cut that in half. So half of pi over 4 is pi over 8. Let's cut that in half again. So that'll be pi over 16. So 1 pi over 16, 2 pi over 16. This will be 3 pi over 16. Okay. So let's see. Tangent normally starts out. Let's see. Tangent starts out with at an x-intercept. So it'll be x-intercept. So it'll be x-intercept, then slope of 1. So here I'm going to go to 1, or I would normally mark a 1 here. But I'm taking that 1, or how about I graph them side by side? Let's put the 1 here for right now. So, and then it'll be see, x-intercept, so slope of 0, slope of 1, infinite slope. Then slope of -1, slope of -1, slope of -1, and then slope of 0. Okay, so the graph here will come up, it'll be down, and it'll come back up and hit 0. So here's the graph of one period of just 3 times tangent of 4x. But now what we're doing is we're taking all these outputs and we're multiplying them by 3. So you could just, I'm just going to change the scaling here. So this output won't be 1 anymore, this output will be 3. And this output here will be -3. And if you wanted to graph it, keep going this way, it would be -pi/6, about -pi/8. Can mark this here. And here's a graph of 3 tangent of 4x. Okay, let's do one more. How about we graph at least one period of, how about y equals, how about -1/2 times the cotangent of, how about, I don't know, let's say how about 2/3 x. Okay, go ahead and pause the video and give this one here a shot. Okay, let's do it together. So the first thing I'm going to ask myself is I'm going to ask, what's the period of this function? Okay, so I have 2/3 times x. So you can either take pi and divide it by 2/3, or you could think that the period of cotangent is pi. So I want the argument, I want to know when is the argument, when is 2/3 x between 0 and pi. I could solve for x, so what could we do? We could multiply everything by 3/2 to get that x is between 0 and 3pi/2. So our period will be 3pi/2. Okay, so let's sketch this. Let's move it over a little bit. Okay, so the period will be 3pi/2, so let's move over here, 3pi/2. Let's cut that in half. So if I take 3pi/2 and cut it in half, I'll be at 3pi/4. So here is 3pi/4. Let's cut that in half again, so I'll be at 3pi/8. One 3pi/8, one of these, two of these. Now this will be 3pi/8, so I'll be at 9pi/8. 9pi/8. Notice that would be 1, 2, 3. If this was 4 3pi/8s, notice that this would be what? 12pi/8, which reduces to, what, 4 goes into there, 3 times 3pi/2, so we get the same thing. Okay? Okay, so let's remember how cotangent works. Cotangent starts out with a vertical asymptote. Okay, remember I'm kind of skip one, so it'll be, or if you like, it'll be, let's just do it like this. It's going to be vertical asymptote, then it'll be x-intercept, then vertical asymptote. Okay. So normally I would have a 1 here, so it would be vertical asymptote, and then it'd be a 1, and then it'd be x-intercept, and then it would be -1, and then vertical asymptote. But I'm going to need to adjust these, because what I'm doing is I'm actually multiplying the outside of the function by -1/2. So this output won't be 1, it'll be -1/2. So a -1/2. So this spot will actually be right here. And over here it's usually a -1, but I'm multiplying it by -1/2, so the output will actually be 1/2 right here. And now I can piece together the graph. And here's a sketch of one period of negative 1/2 cotangent of 2/3 x. Okay. Let's go ahead and let's do an example of when it's shifted. Now, I'm not going to care too much about graphing the shifted versions of tangent, cotangent, cosecant, and secant, but what I mostly do care about is you being able to recognize from the formula what the period of the function is and how it's been shifted. So let's do a couple examples of just recognizing what the period is and recognizing what the shift is. Okay, so as an example, let's find the period. Find the period and horizontal shift of the following. Now, something I'd like to mention is sometimes you might see horizontal shifts. Sometimes they, in terms of trig functions, they sometimes call this a phase shift. So you might see that in some textbooks. A phase shift. Okay. So let's go ahead and let's say we have the first example is y is equal to, let's say it's 1/2, let's say it's, I don't know, cosecant of 1/4 x plus pi over 6. So what we want to do here is we want to recognize what is the period of this function and how has it been shifted. Go ahead and pause the video and try this on your own. Okay, let's do it together. So what I'm going to recognize here is a common mistake here is to think that I've actually shifted the cosecant graph since I'm adding pi over 6. You might be tempted to think that I'm shifting it to the left pi over 6 units. Careful, that's not true. Because I'm adding pi over 6 not directly to x, I'm adding pi over 6 to 1/4 x. So to see the true shift, I need to factor out the 1/4. So 1/2, and then we'll get cosecant. If I factor out a 4th, let's see what we'll be left with. Okay, if you have trouble seeing how to factor a 4th out of a 6th, what you can do here is use the best trick in the math book, which is multiplying cleverly by 1. So imagine that there's kind of this extra 4 times 4 in the top and the bottom. So I'm really just multiplying this by 1. So if I'm factoring out a 4th, I'll just factor this 4 out of the bottoms. So I'll be left with 1/4, 1/4, and then I'll have an x plus, well, I factored the 4 out of the bottom, so I'll be left with 4 pi over 6. Notice if this 1/4 factors back in, the 4ths will cancel, and I'll be right back at pi over 6. Or we could write this as 1/2 cosecant of 1/4, and how about x plus 2 pi over 3. From here, we should be able to quickly see the period and quickly see the phase shift or the horizontal shift. Okay, so let's take a look at this 1/4. Okay, so what we want here is for cosecant, remember the period of cosecant is 2 pi. That's because the period of, let's see, what's the sine? Cosecant is a reciprocal of sine. Since sine is a period of 2 pi, cosecant also has a period of 2 pi. So we're going to take 2 pi and we're going to divide that by a 4th, which is the same thing as 2 pi. How about 2 pi over 1 times 4 over 1? Or we have a period of 8 pi. So we have a period of 8 pi. Okay. Let's take a look at the shift. Okay, so if we're looking here, specifically at this piece, this means we're shifting, let's say, what are we shifting? We're going to be shifting to the left. We're going to be shifting to the left 2 pi over 3 units, because I can see that 2 pi over 3 is being added directly to the x value. So it'll shift it to the left 2 pi over 3 units. So we could say one of two things. We could say the horizontal shift is how we could say? We could say left 2 pi over 3 units. Or you could say there's a phase shift of negative 2 pi over 3. So we have a phase shift. A phase shift of, we would say, negative 2 pi over 3. And there we have it. Let's do one more example. Okay, so let's say we have the function y is equal to, I don't know how, let's do 5. Let's do, how about tangent of, how about, I don't know, let's do something ugly. How about 5, 6 x plus, I don't know, how about pi over 4 or something like this. Okay, go ahead and pause the video and give this one here a shot. Okay, let's do it together. So we need to recognize the period and the horizontal shift. Let's actually go, I put a plus here. Let's actually, I don't know, sorry, let's put a minus here so it's a little bit different than the last example. Okay, so what I'm going to do is I'm going to first factor out the 5, 6. So 5 tangent. Okay, I need to factor out the 5, 6. Okay, so what we'll be left with, how am I going to make this work? Well, I mean, you could do this. You could put an x here, and you could put minus. You could put the reciprocal. You could think of 6/5 right here times the pi over 4. So when this 5, 6 multiplies in, the 6's would cancel, and the 5's would be canceled. I'd be left with pi over 4. You could think that I had, like, I don't know, an extra 6 and an extra 5 in the top, an extra 6 and an extra 5 in the top. So I took out one of those 5's, and I took out one of those 6's, and that's why I was left with 6/5 out front. Okay, so we'll get 5 times the tangent. We'll get a 5/6. Okay, so let's see here. This will be x minus, what will this reduce to? So what? This is going to, the 6 and the 4 make a 3/2. So I think I'm going to get a 3 pi over 10. I would agree. Okay, so let's take a look at a few things here. So first, the period. The period of tangent is pi. So we'll do pi divided by 6/5, or this will be 5 pi over 6. So here's the period. We'll write that over here. The period will be 5 pi over 6. Okay. And now if we're looking here, what we have here is we have a shift to the right by 3 pi over 10. So we might say that there is a phase shift. There is a phase shift of positive 3 pi over 10. And that's the answer. Okay. So that's all I have for this video here. We're finished with graphing all of our trig functions and their transformations. In the next video, in the next section, we'll be talking about the inverse trig functions. We'll see you there. Take care.